a simulation software called Athena, which allows you to watch inside the window at the gas. This window has been filled with air, and you will see the first method, which is a float filling method using a straight lens at the bottom left end. You can see the outlet is just above, and we use a very high speed. The speed is 72 liters per minute. You will see in a few seconds the flow of gas entering. What you've been watching is the real-time filling. The yellow is the krypton, which is the gas being used here for its better insulating properties. And the red represents about 50% filling grade. So krypton has flown around the window back to the inlet, to the outlet. The middle of the pane is not filled properly. Also, a lot of gas has been lost during this process. After 5 seconds more filling, that's what we obtain. Again, the filling is not perfect. The filling grade is only 70%, and 30% of the krypton has been lost. Let us try to improve this method. All most efficient techniques today use the concept of laminar filling. The principle is to reduce the speed of the gas at the inlet so that the weight of the gas can be used to push the gas from the bottom to the top. This is an example of an ideal process. You can see the gas flowing from the bottom to the top. The lens here was a very long lens pierced with several holes so that the gas is dispersed all the way. Now you can see that there is some air left at the top, and if we continue for more than 5 seconds, up to 10 seconds, we can get rid of most of this air. So here the filling grade is much better. It is about 90% after 5 seconds, and after 10 seconds, of course, you get a very good filling grade, but again, you've lost almost 100% of the krypton. So here we should stop at 5 seconds, which gives a very good filling already. Let's try to do something more practical. Here the filling lens is 10 centimeters long with holes on all its length so that the velocity of the gas is reduced. You will see that the flow will be vertical. The gas will go up, but because of its weight, it will go down again, and we will be able to obtain a kind of laminar filling. So this is an intermediate case where we still have some mixing in the middle, you can see, and we still have some air at the top. The filling grade is 85% at this moment, which is already quite good. If we try to continue the filling, we can't get rid of the mixing in the middle, and the filling grade improves to 90%, which is not a big gain. So we suggest that the filling should be stopped at 5 seconds, where the filling losses of krypton is only 15%. Let's now have a different look at what happens in the window. This is a view of the flow lines of the gas. You will be able to follow how the gas moves inside the window more precisely with a reduced time. So in a few seconds you can see the gas flowing up and then flowing at the bottom of the window and up again, making this kind of whirl in the middle. And from this picture you can understand where the problem in the middle of the window comes from this whirl that you can see. Let's now look at other questions. Have you ever wondered whether a feeling from the top was possible? We have been studying this possibility, and you will see some examples with these cases. In the next simulation, the flow rate is 27 liters per minute, and argon is filled from the top at the right end. The outlet is also on the top on the other side. So you will see in a few seconds the gas going down, and what happens is that the laminar filling does not happen because the gas goes back up to the outlet without flooding the window like in laminar filling. So the problem is again the excessive speed of the gas at the beginning. So you can see that after 20 seconds the average filling is only 70%. So again we try to reduce this speed by using a longer length. Here it's a 6 centimeter length that you can see at the top. After some simulation time you can see that the result does not really change, because what happens is that the gas sticks to the wall, to the right wall of the IG, and the speed of the gas is not really reduced inside the window. So we tried with even a longer length. Let's have a look. Again, the gas is sticked along the wall and the speed is not reduced. So that results will be the same, and we cannot achieve a laminar flow by this method. When filling with krypton, we cannot afford such high losses. So what we are now trying is a very quick flow of argon, which is a kind of a float method with a rate of 55 liters per minute, in order to reduce the time of filling with argon and have more time to be used for krypton afterwards. So after this first filling, we are now looking at the inlet of krypton. So this is actually a mixture of air and argon, and you will now see the krypton going into the window. And the krypton will be filled with a speed of 27 liters per minute. This process allows for a rather quick filling, 30 seconds altogether, with argon first to get rid of the air, and then krypton. The final filling grade is 60% krypton in argon. There is almost no air left. So this can be interesting to get the krypton-argon mixture inside a window. But there is no way to get a good filling method with pure krypton inside by top filling. This last example is the most well-known filling method, using laminar filling and filling from the bottom. The inlet has been simulated here by a small square to represent actually a very ideally diffusing lens. You can see that the speed has been reduced and that the filling after is very smooth, and we obtain this laminar filling that we wish to have. The filling grade is already 90% on average. The loss is therefore only 10% of krypton. If we want to obtain a better filling grade, above 95%, for example, we should continue the filling for a few more seconds, and that's what we are going to do in this example, so that we get the correct filling grade. So after 36 seconds here, we have obtained a filling of 95%. The flow rate here was about 15 liters per minute. A similar filling method can be used up to 30 liters per minute using high-speed filling systems. The results are almost similar in terms of filling rate, losses being a little bit higher. Air Liquide is willing to continue this research with the window industry and to optimize the filling methods or to adapt them to the needs of insulated glass manufacturers.